or maybe the other way around, hopefully, and we'll see. Where are we now, right, in the course? I think you have a basic understanding, especially with today's practical in mind, of what the basics are of one of those standard location-based fMRI experiments, right? So you have a specific question, you ask, where is brain activation stronger for this than for that? You get out a 3D image that represents like a T contrast or something, and then you work with that. So that's good. And that's like the basics for many fMRI experiments that people do nowadays. At the same time, that has been the sort of foundation of the field for like at least 10 years. And so what that means is that we can now take a step into more modern approaches to how to analyze brain imaging, right? And so what we're going to do is take a step back, because the modeling that we do is no longer necessarily like a GLM based. We just have to sort of reconsider the idea that well, we're just looking at four-dimensional signals in fMRI, right? And what else can we do with these four-dimensional signals? And one of the things that we'll talk about today is how to analyze those in as patterns instead of trying to model the time courses. And there's some other things that that we'll also talk about that have to do with things like connectivity, like how does one brain area connect to another. All of that also goes back more to this idea of, okay, we have like a brain worth of data, right, every second or so, and how do we analyze that? Just that we have 4D data, how are we going to come to terms with that? And then people have come up with different approaches to analyze data from that perspective, like a more data-driven perspective. And today we'll talk about one of those, namely the patterns. I'm saying space and time here, or time and space. We'll mostly talk about space, so that is the pattern across voxels in space, and not so much a pattern over time. But I have a little tidbit at the end that does specifically focus on time, which I think is interesting, just as a thing. Also, so after this lecture, there'll be a practical, right? Also here, right? So there's 2 rooms devoted to that, one on the 7th and one here. Let's stay here for now. Yeah. Great. So yeah, what we've talked about until now, right, is this very simple setup where you put someone in the scanner, right? And you show them something. Because you put them in the scanner, what you get is data, and when you pre-process that using that GLM that we talked about, you do a bunch of post-processing, such as statistics, right? And then you end up with a beautiful blob somewhere in the head. Yeah. And this is what people call mass univariate or just univariate analysis of fMRI data. Right? So you're doing, in principle, exactly the same analysis across all of the voxels in the brain. What do you call it? Univariate. Doing it on all voxels, right? And this leads to these patterns, which people sometimes refer to as a blobology, right? This location approach to fMRI. This is the love region. This is the hate region. This is the my ass is itching region of the brain. Blobology because, you know, well, what you're doing has to do with just saying this function goes there in the brain. The question is, how much does that say about mechanism? Yeah. And so one of those things that we're going to be increasingly talking about is how does the fMRI, doing fMRI allow us to say something about the mechanisms the brain has to process information. Yeah. And so if we just do blobology, what we are looking at specifically, right? So we could take the voxels from a specific region of the brain. We can call that a region of interest. and then average the activity for different conditions, right? So this is one way in which you can say, I'm interested in this specific region of the brain, and I have more activation during fearful condition than during the love condition, for example, right? And this looks a lot like your standard sort of psychological experiment outcome. Yeah? So you've just designated where is my blob, and then I'm going to do an analysis on the amplitude of the amplitude of the signals in that region. Of course, you do this this part and this part on different data sets, right? Otherwise, we go into voodoo correlations and that sort of thing. But what we're interested in here is just the amplitude of the signals, the strength of the activations. Yeah. Now, there's a few problems with this, and I want to go like iteratively through a bunch of them, because if our question really is to try to use fMRI as a tool to understand the mind, okay, where are we getting on that quest by using fMRI in this way? And the rest of the lectures we'll actually go into other ways in which we might be able to better really understand how the brain gives rise to the mind using fMRI. The problem that I'm first going to talk about here is what is referred to as the thresholding problem. Right? So if you have, and you'll see this in the practical, right? If you've run a contrast, you get a bunch of t-statistics, one for every voxel in the brain. And what happens is you get this whole distribution of t-values. They're distributed, who knows how, depends on your experiment, depends on your brain. But what you can do then is say, oh, I'm interested in those regions that have a t-value higher than x. So let's say that that's 3. It means some p-value given how your experiment worked. And then you might find a single blob, right? And you might say, ha, this is that single love region, right? So this concept x is, I can see that it's locally represented in, let's say, some region left dorsolateral prefrontal cortex. This happens a lot, right? This is exactly that. Hey, it's that blob thing. But it's important to realize that you have this whole brain worth of t-values, and what you've just done is you've applied a more or less random or arbitrary t-value threshold. And so what you can do is just lower that threshold for fun, right? Or get more data per subject or more subjects so that also will increase your t-statistics, or do some denoising that will increase your t-statistics. And at some point, you'll see that there's other regions that also surpass the threshold. And so I can lower my threshold, or something else can increase the statistics. And at this point, we have this entire network of stuff happening in the brain. And the way that you generally then see people talk about that in the literature is, well, this concept X is globally represented in this network of regions, for example, again, that dorsolateral prefrontal cortex, but also now the precentral gyrus, temporoparietal junction, anterior temporal lobe, for example, right? And these sound like quite different sorts of conclusions, right? One is very definite, like, hey, this is where it's happening. The other is like, yeah, it's very broad and yeah, just a bit more undistinct, if you will. But it's the same data that's underlying this. And yeah, you could say like, here I'm being too lenient, maybe here I'm being too conservative. That's a statistical thing. But getting better data will, if you start out with this, will also give you that, right? So there's a slight problem here, namely that the type of conclusion that you would want to draw about brain function, it gets a bit difficult to very clearly think about. You want to say something very definitive, but it turns out that there's some inherent vagueness there that you might consider a caveat even. Yeah, is that function now a local thing, or is it a global thing? And how does this help us understand how the brain is organized? Yeah, it's an open question, this. Certain things must happen locally, others must happen globally, but how does fMRI help us understand how the brain does it? So there's a slight problem there, perhaps, that I hope you'll see how subsequent lectures, like certain subsequent topics, are starting to address this specific sort of vagueness. Okay, so one sort of philosophical thing that people hold against just running a general linear model analysis and then getting these t-statistics and getting these blobs in the brain is that even if you go with like what was just on the left side of the screen, right, this location of the brain does this, you end up with something like this, right? We all know these, I have one in my study even, these heads, these phrenology heads, right? So all of the mental capacities and functions are just distributed as a sort of patch on the skull, like this is there. You know, the one where Homer has a very big beer and donuts region, Homer Simpson. Anyway, so this is like old pseudoscience, right? This phrenology. And so what this gives us is that this notion that fMRI might be doing a little more than just neo-phrenology, right? So we're now just also saying, yeah, certain regions are doing this one thing, right? And we run into another conceptual problem, which I over eagerly just popped on the screen here, is that especially if you go into the higher levels of the brain, like into frontal cortex, for example, we might not just really know what is the word that goes with the region there, right? So even though a region might have a very specific function, that does not mean that we have a word to describe that specific function. Okay? So all of these labels are preconstrued sort of human constructs, and it's just a matter of debate or question whether these even align with what a specific brain region might be doing. Right, and this is a very important question that I think sort of we need to learn to turn upside down, turn on its head. Right, as we do fMRI, we might be interested in like, oh, how does fear work in the brain, right? And yeah, that might be cool, but the brain might be doing things that we now call fear, right? That fear, in some sense, is not the best word to describe it. This is going to be very vague, right? So, but does the concept of fear actually align with a specific brain mechanism, or are brain mechanisms shared, for example, between fear and pleasure? Or you know, we all like to watch, well, not everybody, but a lot of people like to watch horror movies, for example, right? And so the question then is, are we so confident in our sort of subdivision of cognitive constructs that we are going to just fundamentally apply it to the brain, right? Does that make any sense? Or do we need to try to learn what these actual cognitive constructs should be from the brain? Yeah. And so this localization approach, what it does is it tells us, or what it sort of implicitly does is it says, I'm very confident that this word that I use in my sort of talking about how cognition works, that I should be finding that in the brain, one-on-one, like there's this mapping there. And that means that we sort of presuppose a certain structure of cognition, and there is no rule in the world saying that the brain should adhere to what we think it should be doing, right? It might be doing something completely different. And if there's anything that we learn from science in general, is that on the whole, the concepts that we started out with trying to describe a certain phenomenon are wrong and inadequate when we dive into how things actually work. Right? So we have to be aware of the fact and the likelihood that when we start diving into the brain, we will also need to sort of redefine the concepts that we use to describe cognition, even though that's not what we wanted, right? We just wanted to use fMRI as a beautiful light box of where concepts are in the brain. It is going to tell us that things work otherwise, perhaps. Anyway, that was all a bit philosophical. I'll try to get back to that later on in the lecture, and I'll also try to hook into this sort of conceptology over the course of the next lectures when we start talking about other ways in which we want to try to understand what fMRI can tell us about how the mind works. Okay, so the problem was that I would be talking about patterns, and now I'm just blabbering, right? So let's talk about these patterns. Seems like this is now quit again. So, yes. So, I talked about average responses, right? We're interested in the strength of a response, right? Is it activated more or less? And just to show you an example, you can have a specific region of interest, for example, in this case, a D4, which is a visual region that's color sensitive. So we know that if we show people a color movie versus a black and white movie, this region will light up if you ask for the difference between the color movie and the black and white movie. So what this means is there's a lot of color selective neurons in this brain region. Now, if we're interested in the type of processing that this brain region does to colors, right? What does it do with the colors? We might be tempted to ask like, okay, but maybe it's going to respond more strongly to red than to green or something like that. Yeah. So what we can do is we can average across the entire brain region and see, is there a stronger response to red or green? That may be what we're interested in. But it turns out that in general, the mean response doesn't really tell you much about what's happening inside an ROI, and that's because you've just explicitly thrown away that information. So no average response difference. But maybe we can still find evidence of color selective processing in this region if we do something else. If we focus not on the average response, but on something else. And you already know what it is because it's the title of the lecture, but I'm taking it slow. Now, one slight philosophical thing that I just want to put in is like this reverse inference problem that you've also seen, I think, maybe in the YouTube videos, right? We would want to say from what we measure in the brain, what happened in the mind, right? What was the cause of that brain activation? All right, so we can be very broad about that. It was a color stimulus, right? That's some statement, but we want to be more specific, right? We want to be as specific as possible in this sort of reverse inference type thing, right? We want to be say things like maybe it's a yellow stimulus, or maybe it's a yellow cab, or maybe we want to be more general or in a sort of cognitive sense, right? And the question here is, what is it about that visual stimulus that we're showing that produces this effect in the brain? Right? We have to know that in order to be able to go from our brain measurements back to what we think happened in terms of cognition, in terms of stimulus, and so forth and so forth. Yeah. So when we talk about these univariate analyses, right, these general linear model analyses where we get these t-statistics, it doesn't really allow us to distinguish different stimulus types within an ROI. So D4 is color, but it doesn't allow you to say whether something is red or green from the average activation. And it's also very, very difficult to perform reverse inference from a pattern of both responses that you get. What was your subject thinking? What was your subject experiencing? Well, it's very hard to discern that from this framework, right? So we have a bit of a problem there. Now, there are two ways in which we can address this, or in which that we're going to highlight how we address this. This forward models is what we do when we form explicit models, computational models of what the brain does, and we try to fit them on brain activations, and thereby, whenever we see a pattern of brain activation, it tells us what would be the case in our model if this pattern of activation were the case. And then we have a handle on what happens in terms of cognition. And we'll talk about that a lot more in further lectures. So if that was a bit vague, don't worry about it. In this lecture, what I'm going to do is talk about pattern classification. That is, instead of taking the mean response from a region of interest, we'll take the pattern of responses and see how far we get if we just use that as the input to an analysis problem.
Was the region of interest in the previous slide B4, or was that larger than B4 and the thing that you're interested in is?
Well, for the point, you can just assume that everything that's all V4, just talking about just V4. In general, what you do is this concept of ROI, this region of interest, is extremely broad, and I'll show you a bunch of examples on how that can be a very flexible concept. It's just any bunch of voxels that you're interested in at present. Yeah, so it can be anything. Yeah. I'm going to move to the next part of this, where we really go into the types of analyses that people perform on these patterns. So, any questions, more philosophical? Why are we even doing fMRI if it can't tell us how the brain works, sort of thing? Any questions? Yeah.
Various analysis can tell us anything about the specific Boolean average of interest. How do we know that our interest is specific?
That it's like
Like if that's a quarter of P4, for example, means P-folks and red, a quarter of the P-folks and blue, instead of just taking the entire P4.
Yeah, that's an excellent point. So, what you're interested in is getting to smaller and smaller ROIs, right? And then maybe there's such heterogeneity across these different smaller ROIs that it allows you to say, hey, but this is a red stimulus because this region of interest is like higher, more strongly activated than this region of interest, right? And what you're aiming for is exactly the notion that underlies multi-voxel or multivariate pattern analysis. So yes, we need this heterogeneity to be able to infer this. And in principle, you can get the heterogeneity from the results of a GLM analysis, right? So you can get differential beta weights across a region. It's just that when we are doing univariate analyses, we don't care about sort of the fluctuations, not about the heterogeneity. We just care about the global value. Yeah. So excellent point. That's exactly what this type of analysis tries to do. And so it's going to help us, right? It's going to help us solve a couple of these questions that we have, like specificity, that sort of thing. Yeah, so good point. Yeah.
Maybe my sure neochronology. So basically, the confusion or the conceptual differences pop up when you're looking at more abstract concepts and not necessarily at a much lower level concept, right? We can, to an extent, be very sure what's happening or what we're looking for conceptually when it comes to lower level abstraction. Right? Maybe just the fact that color exists and kind of correlates with the physical phenomenon. Only the concepts of maybe like fear and maybe love. That's where the differences pop up, right?
Yeah. And this and so this relates very much to questions I think you had earlier on also, like if we wanted to estimate the HRF for a given region or voxel, right? We need to be able to say now it's active and now it's not, right? So for M1 or for B4, for example, you show a colored stimulus or have someone tap their fingers, and then you have your impulse, your very brief, very strong activation. But for these regions that we don't really know what their role is cognitively, it's very hard to come up with an experiment that just gives it like a 1 second on, all seconds off sort of response, right? And so you see this sort of interaction between knowing what a brain region does and then finding out what it does, right? The more you already know, the better you can use that knowledge to dive into it more deeply. This also means that these very high level regions of the brain, for example, frontal cortex, we do a lot of research on it, but we don't still really know how we should categorize what they are doing, right? And yeah, so we don't really have a specific word that we can attach to specific regions of interest, for example, in frontal cortex. It becomes hard to categorize. Yeah.
You were talking about how reducing price of the ROIs is our aim in a way. Does it mean that we are just remapping the technology in a much more detail?
Ha, yes, that's a good point. So, and this is, but you're skipping to the end of the lecture here. Yeah, so this is a very critical question, and it's a very good sort of philosophical question, but I'll try to get back to it towards the end of the lecture. I think that would be more productive. Right now, I just want to take your comments, right? Like subdividing ROIs. We can subdivide ROIs and then say, the left part is more red and the green part, or the right part is more red green, red? I forget. Anyways, I've been sick. And if we take that further and further and we subdivide further and further, what do we end up with? We end up with our voxels, right? And so here we are. We just want to use the pattern that we already have from the measurement, which is the pattern across voxels. Yeah. I'm going to show you a bit of a sort of historical introduction into how people started thinking about using these types of patterns. So there's a few, and this is also in the pre-lecture reading material if you want, like, I'm not going to quiz you about it, but the question is, I guess in many contexts, right? You just want to ask the question, is there some kind of information processing in the brain, in some region of the brain, or in the brain as a whole? Can we find evidence of that? Just a yes/no question, right? And if that's our question, it's awesome. Now, I'll show you a very poignant example of when we have such a question, and that's in patients that have, for example, had a car accident and are in what we call a vegetative state, which means that they cannot respond to outside world stimuli. Right? They can't even blink, sort of thing. And in these patients, right, so they're in a hospital bed in a comatose situation, but we don't know whether they're actually in a coma or not. And we don't know what level of self-awareness they still have, right? They could be completely locked in. And this can happen for all sorts of reasons. A friend of mine had a bleeding on the brainstem at some point, and also had this locked-in period where she was locked in for a month, couldn't move. She could only blink with her left eye or something. She's like almost fully okay now, but this happens a lot. When you're locked inside your body, you cannot control your body anymore, and you're still fully aware of what's happening with you. So in this case, to answer this question, outside of the story otherwise, the question that you want to ask is this person conscious or not? And to what extent are they conscious, if yes? Yeah. And so in this experiment, which is a really groundbreaking experiment, they asked these patients, sort of presuming that they would still hear the question and understand the question, they would ask them to either, for 20 seconds or 30 seconds, just pretend to play tennis. So can you pretend to play tennis for 30 seconds, right? So you can all close your eyes and just imagine that you're serving and that you're running up to the net and trying to volley, and then doing it again, having a long rally on the baseline, that sort of thing, right? You can imagine that. What that means is that in a healthy control, for example, regions in the brain like the supplementary motor area that do motor planning will become active because you're actively engaged in planning, imagining movements. You can also ask people to walk around their house, go from the kitchen to the bathroom, then to their bedroom, then to the cellar, and then back to the kitchen, and just repeat that over and over, and once in a while, change direction. Yeah, just walk through your house. Now, there are specific regions in the brain that do spatial navigation, right? And when you imagine yourself walking through your house, you're going to get a whole different region of the brain active. Now, we're talking about a pattern in the brain, yeah? Well, let's say we use as an ROI the entire brain, yeah? And our question is not, can people imagine tennis or playing tennis or navigating? Let's assume that they can, but let's assume that this gives us a different pattern in the brain. Can we then start using it to ask questions and just say to a patient that we can't otherwise talk to, say, if the answer to the next question is yes, spend the next 20 seconds pretending that you're playing tennis. Or if the answer is no, spend the next 20 seconds pretending that you're walking around your house. And this way you can fire off a whole series of yes/no questions to a subject. Even if they are completely locked in, they cannot respond to you outwardly. They can use their imagination, if you will, and your possibility of reading it out with the MRI scanner to get answers to those questions. And it turns out that that is possible, right? So they could really start querying, these researchers, the sort of mental state of the patients that they wouldn't have access to otherwise. It's a nice example of how fMRI can be used as a sort of brain reading device. Yeah. And this is really also one of the first studies that brought this idea also to the public's attention, right? That you can't just use fMRI to say there's a blob here and it's a love blob or whatever, but you can also start to sort of ask questions about what the brain is doing, right? And thereby use fMRI as a brain reading methodology. You can immediately see like how, you know, lie detection fMRI then started popping up and all that sort of thing. So the idea here is that we cannot just distinguish these very broad mental states and use the entire brain as a region of interest, but we can just subdivide the brain into smaller sections, right? And then the question becomes more something of a yes/no question regarding whether a certain type of processing is happening inside that specific brain region, not the brain as a whole, right? So the example with the vegetative state was the whole brain being the region of interest, and now we can just adapt that to go to the level of the single region of interest, right? So what we're going to do is, instead of doing this univariate thing where we're interested in the average activation or average whatever it is that we measure with fMRI inside a region, what we're going to do is look at the pattern of activation inside a region of interest. So just some vector of responses instead of just its average. Now, it's important to realize then that if we do univariate analysis, what we're doing if we create a bar chart like that is we're throwing away a lot of information already, right? Because the distribution of beta weights in this case, perhaps, can carry a lot of information at the voxel level. And it's specifically that distribution of beta weights that we're trying to work with. Yeah. So specifically, what you could do, and what has been done, and what's the sort of most standard way of doing this, or what we started out with doing, is to say, okay, I'm going to show a bunch of faces and I'm going to show a bunch of houses. Look at these 9 voxels, which is a small region of interest. Yeah. And then say, okay, what pattern of activation do the faces have in common? What pattern of activation do the houses have in common, right? And if I can identify such a pattern, then this means that there is a different state of activation for faces versus houses. It means that I can start using this region of interest to read out whether a face or a house is being shown to my observer, right? Impeccable logic, right? And so if you look at our brain, I wasn't using houses and faces for nothing, right? If we zoom around here, if our region of interest is large enough, right? If, let's say, this is our region, if this is our region of interest, it has both orange and blue in there, right? So that should give us enough information to decode. But there's an ongoing discussion about what the level of detail is that we can expect this type of thing to work on. And I won't go into that. It's a bit detailed, but you see that these patterns do exist, and if you can see them at the broader level, then you know that you'll be able to perform an analysis like this. This is from the first paper that did an analysis similar to this. What they did is they showed a whole bunch of different categories to subjects. And then what they would do is take a specific region of interest in the brain and see whether they could find this consistent pattern within a specific category that would disappear when comparing patterns across categories. And then if you look, for example, at face selective regions and faces, you see that it has a very consistent set of correlations within category, but very little between category correlations. Yeah. And so similarly for houses, right? What this shows is that this region of interest has a consistent pattern, higher correlations within a specific category than between categories. And so this then tells us that, yes, this brain region, however large it is, does differentially process information from faces and houses. And by virtue of picking up that pattern, I can see from someone's brain activation, are they looking at a house or are they looking at a face? Now, I'm taking this relatively slowly. I don't want to get into the specifics. There's a whole like old AI field devoted to this sort of pattern analysis. I'm just going to go through the concepts. And later on, I'll show you how this type of analysis, if you drive it further and further, what it allows you to do. So the gist of this type of analysis is very simple. I was just in the previous slide, I was talking about correlations, right? We have a specific pattern. I'm just going to look at whether that pattern exists by correlating the pattern of activation between two presentations of the same type of stimulus and across types of stimuli, right? And if I find a higher correlation within the category, then that's what I pick up. So a very simple type of analysis. But you can do this in a much more complex way. What you can do is you can train a classification algorithm to find some pattern, whatever it is, between two types of stimuli, right? So I have stimulus 1, some pattern of bold activation, stimulus 2, some pattern of bold activation. And I use an algorithm to find a difference in pattern between them. And then I have a different set of data on which I test whether my classification algorithm has learned something. So based on this pattern that it's tried to distill, the algorithm would predict stimulus 1 or stimulus 2 was shown, right? House or face was shown. And then what you do is you express the performance of that algorithm as an accuracy, right? So that's percentage correct or area under the curve, things like that. And that then gives you a measurement of whether a certain brain region, whether a certain ROI from which these voxels were drawn, contains information processing relevant to the categorization and separate the patterns. Very simple logic, but it works. Just to give you a quick, sort of very slow introduction, and then I guess we'll have a break. How does this sort of thing work? And what I'm going to do is show you not a 100-dimensional pattern, but just a 2-dimensional pattern. So 2 voxels that we're recording from, just to give you an intuition as to how this works, right? So we have a beta weight in voxel 1 and a beta weight in voxel 2. Voxel 1 and voxel 2 are also shown there. And their values are going to be filled in with yellow or red. So the stimulus that we'll show here is going to appear there. And we'll have a specific point in this 2D space that represents the pattern of activation that is caused by a specific type of stimulus. Yeah? So, for example, if we show a car, we get a high value, a high beta weight in voxel 1 and a low beta weight in voxel 2. And what that means is, of course, that it ends up there. High in 1, low in 2. That's where it is in that 2D space. If I show a face, this is a very old picture of me myself. My former PhD student made this slide. So yeah, and so it turns out that this voxel now, voxel 2 now responds very strongly, and voxel 1 responds not so much. So I end up over there. So this is a car, this is a face. You already see the sort of thing that this that a classification algorithm would pick up, right? So that's Dan, that former PhD student of mine. Here's another car. The pattern of voxel responses just ends up in a specific corner of that space. This is Jan Theeuwis, for those of you who don't know him. He is definitely a face. Or he has one. I mean, sorry, he's not just his face. Not just a pretty face, Jan. Sorry. Here's another car. It ends up in the bottom here, right? And you definitely see the pattern that a classification algorithm would pick up, right? What the classification algorithm would do, and many of you that have done a machine learning course are now yawning to the max, I get that. But what a classification algorithm would do is it would find a line to separate these two populations of responses, and thereby say, if I get a new stimulus, I can say its carness or its faceness is just how far it is away from that boundary that that classification algorithm drew. Yeah. And that means that when we start testing the classifier, we now have this line because that's what we trained, right? That's what we found during training. And now we can start showing specific patterns again, right? So, specific stimuli that then cause a specific pattern, and it ends up in a specific corner of that space again. And now we know, the carness, right? It's positive carness and negative faceness, so it's a car. And this is correctly classified. If we show a face, here we are again. Yeah, correctly classified, right? But and this is a funny example, right? But what does this do? Well, it's going to be somewhere in the middle, right? Because it has both a face and it is a car. And depending on the category that you just used as input, you will either say this is correct or not, right? So this is how that sort of sequence of events works, right? If you set up a pipeline, you first train it, and then you test it on how to set data. And what it nicely illustrates is that this type of approach, it can pick up patterns, and they can do so in very complicated ways. I'll get into that in a bit later. But more importantly, like philosophically, what it means is this approach really depends on your ability to categorize things, right? And if things are more complex and you have trouble categorizing them yourself, this sort of analysis stops making a lot of sense, right? This is both a car and a face, so it sort of eludes the distinction. Yeah. I think let's have a break, and then let's be back here in like 10 minutes or so. I don't know. Let's take a long break. I've been sick. I need a break.
Now?
Kind of like the same, well,
Yeah, dude.
I heard the half sentence. That was enough.
I was wondering, like, the level of depth from AI to go into.
Oh, yeah, well, more and more. So,
Yeah.
you have to remember that this whole thing, it exploded around 2007 and 8 sort of thing. That's way before ImageNet, right? So, people were still, doing a lot of like diagrams, like, quasi old school AI type things. The state of the art in machine learning was using nonlinear SVMs, more or less. Maybe I'm going for this bit here. Yeah. So, yeah, that's what people use. Nowadays, people do a lot more, really, using GANs, it gets a bit more complicated. But yeah, this is the historical sort of. And yeah, I don't know. It's gonna be, more interesting later on in lectures, because then we'll actually start looking at, okay, how do we, if we're interested in how the brain works, we're going to use the neural network model as an actual model for how the brain. And then you can also, when you can, the relationship between the activation patterns of the neural network and also. So we're going to go into that later. So it's yeah. It's not going to get better. I'm sort of stuck to the whole historical lifeline. But yeah. Yeah, it's sort of, it's interesting, you see these whole fields making silly mistakes, right? If you look back 20 years ago, like what the hell were they thinking in many cases? And you couldn't, there's something new, think about with it, and then there's something else. But to see the young fields and actually see it from the get-go, see it like grow like the trends and it's interesting. Oh yeah, I mean, you see this happening. So this coding type thing really was a moment. More slowly, there's emphasis on connectivities that we'll get into later. Those are big changes. And then now, of course, the whole neural network is mapped onto the brain. It's very simple. Yeah, it's all. The question remains, right? Is there like where are we cutting the corners now that we'll start flipping this up later on? Usually those things are really the sort of linchpins of a new development later on. So that's- But it's a, yeah, those also are the future. It's interesting to, for me at least, that we look back during things like this, starting from phasing. Going further and further, we get learning more and more. So you see that even a community of scientists can be pretty stupid. You know,
Just like.
as they're figuring things out.
It's also gonna get more think about what actually, how things work, the more like into the other the you go, if it's we don't know exactly how how that applies to
Well,
the rent.
yeah, that's what we learned a lot. And that's about certain principles that we can be very confident about. At the same time, yeah, it's a bit of a smudge, sort of everything is sort of. You realize you can find evidence for almost anything. And that's sort of, you know, the things that people like to have these little, you know, nicely fenced off contact. And I think that's sort of starting to disappear, so. It can be a bit confusing. It is to me.
Are people working on making more brain like? In the sense that maybe also the neurons are more biologically thought. Do you know if there's any progress?
Yeah, sorry, you ever go through like slicing neural networks, right? Engineering, that sort of thing. Yeah, people also trying to, not in like transformer like way, but include things like attention and, specifically like neuromodulation, right? So it's clear from the beautiful studies in the crab. Yeah. Gut, that, crab and it's like, there's like a sort of connection of neurons in there. And it's a very fixed neural network. And it turns out that it can have, it can produce like the gut movements of the animal, in like a couple hundred different ways, or different settings, that work best at different temperature ranges and different environments and all that. And so even if you have a neural network, that's sort of hardwired, you can create like stable patterns, activations, that will give similar behavior, right? I suppose also a complicated problem where you have a brain work, you measure a specific pattern of activation. What does it even mean, right? Can it just be exchanged with different patterns of activation and then produce something? What are you looking at? You don't know. So what this, another thing that this sort of finding highlights, if you have some modulators, they can just active and thereby also change function, for example. Right? So there's a lot of interest in meta learning in AI. So tasks, affecting on different tasks that could be people thinking about this sort of neural modulatory tuning of neural networks, like a activation gain type dial that you can change. You can learn something in one and that's dial something so there's yeah. It's well seen now and has like the way that people think about that has also changed in the last 10 years. They're beautiful studies yeah, from where they've done, you can think of, you can think that the single cause is very important. One of the population of neurons, and that is more information than the two. Well, we can let's talk about that another. It's not a brain image thing. It's more of a, but they're beautiful lines of they record like a couple hundred neurons. You actually see that in hundreds of neurons, the activation pattern you can actually project into like 2 or 3D space.
There's a lot of redundant information processing amongst the neurons, right? And you can't actually look at one single neuron and know everything. No. They can switch. This sort of subspace projection allows you to really look at like sort of very beautiful, like the consistent type of patterns, like the Lorentz effect. That's like the thing you can see in the stuff with the neurons as a population, the applies to this sort of dynamical. Yeah. And they're like really beautiful. There's a bunch of nature papers on that in 12. With the show how this subspace projection can be changed as a function of switching tasks. That is not even the stimuli remaining have the same. So, yeah, it's sort of the bit of work that I'm helping do, but I don't have really essential data. Something like this suitable for kind of, yeah. I don't know, not necessarily in my lab, but yeah. No, I mean, I have, I'm gonna get this sort of data, yeah. Yeah, well, yeah, it's just send me an email. This one, yeah. Yeah, I'm sort of looking at this one as well. Yeah, no, this is sort of thing that we're actively thinking about how that sort of thing. That's sort of finding with the like multi-unit electric design. How does that translate to voxels? We have no idea. Actually, it's kind of complicated. But can we do similar things with fMRI? Don't know. Yeah. So anyway, yeah, I'm gonna get people to start the class again. Emma, that's a very nice question. I'll go into that in just a bit. Okay. So just a few specifics. I just showed you a two-dimensional case because it's nice and flat. Right, and you can see where things end up, but you generally extend this to n dimensions, namely the number of voxels that you have, so that can go into the thousands. Becomes a bit hard to visualize, right? So here that separating line becomes a plane, and then people talk about a hyperplane in more dimensions, and so forth and so forth. There's also a whole host of different methods that people use to draw these lines and planes. This is all like pre-deep learning AI, but you can have linear discriminant analysis or support vector machines, or any type of k-nearest neighbor. So you have different methods that draw this line, but the principle remains the same regardless. It is you train this classification algorithm and then see whether it has been able to discern a certain pattern, right? The standard that people use most still is the support vector machine with a linear distance relation. You can also use others, but this one is seen as being simple enough to still be interpretable, although that is something that we'll talk about a bit more. Now, again, I just want to highlight this idea that you always want to separate training and test sets. It's completely trivial for most of you, I hope, but just to highlight this because it's something that this field has
made mistakes in. It's something that I keep reiterating, right? And so you want this classification algorithm to find something real, right? You want something consistent, you want something specific, and you want it to be well, specific being accurate, and you want it to be sensitive to this, right? And you always want to test whether this algorithm performs well on data that it hasn't seen before, because otherwise you get this circularity going, and that's incredibly problematic, right? You can just fit any algorithm on noise. If you test it on the same noise, you will get above chance performance. It's just because it's overfit, yeah? Then, depending on your experiment, you want to, let's say that this is your entire data set. Let's say it's 12 different runs, right? So you put someone in the scanner and you scan them 12 times for 5 minutes. So you have 12 different runs. And then depending on how you've distributed your experiments across those runs, you can do something like gather 3 runs in a row, and then use 3 as a training set, and the 4th of those blocks as a test set, and then iterate through like so. This would be like a k-fold where k is 4. You can also run every run as a test set once, so you just iterate through. You repeat, right? Train again on 11 and then test on 12. Or you can do like a random sampling. This all depends on whether, for example, all your experimental conditions happen in every run, right? Because if one of your experimental conditions didn't appear in one of the runs, then you can't really use it, that sort of thing. Yeah. So this is just a way of separating out these training and test sets. You have a lot of leeway there, right? And this is called cross-validation, just for those of you that did not know this. Now, we're going to get into interesting extensions of this. A few of them, and then into interesting applications of this. So I've been talking about regions of interest. We've had a question about regions of interest, right? What is your region of interest? Well, that depends on what you're interested in, right? And this means that you can say, I'm going to use the whole front of the head. I'm going to use the whole head, if that's the yes, no question that you're wanting to ask, right? But you can also say, I'm going to be just completely flexible in terms of what my region of interest is. I'm just going to take something like a sphere shaped thing like so. I'm going to select all of the voxels that fall inside this sort of selection box and use them for a classification algorithm analysis. And what I can then do is take that and then move it over to the left. And so what I'm going to do is like sort of typewriter that's what we call a searchlight through the entire brain and use a little region centered around every voxel separately as a region of interest. And so what this gives me is a full map of the brain in terms of where information concerning, for example, the difference between faces and houses is encoded, right? Where processing differs between houses and faces. And this is used a lot. If you don't really have a clear idea on what region of interest you would use, or you have a few regions of interest that you know a priori, but you want to do a more explorative analysis, like an exploratory analysis to find, for example, somewhere in frontal cortex, there might be a region that does some difference, then people use this, a searchlight analysis. Yeah. Of course, you can change the size of the searchlight and so forth, but this is the general procedure. You just take a set of these, so an ROI shape like this, it's nice and uniform, and you just run it through the entire brain. You can imagine one big disadvantage that this might have. Just imagine how many times you're doing this analysis.
A delay in response, because when you perform a stimulus, it takes time to respond, and then in that time you might actually move.
Like so, yeah. No, this within this region of interest, you perform the entire analysis. So all of the time points are also in there. It's just that you do this this going through the brain. You don't do it in time. Well, you do it in time in practice, but you do it in parallel. So the analysis that you do is completely identical in terms of its input. It's just that the voxels that you've selected are slightly different.
And multiple testing.
Yeah, so this is a very important thing that, if I know I'm going to do this only in V4, this region in the visual cortex, right? Then I have a single statistical test that I perform, and I can trust the statistics. But I'm doing it 100,000 times here. That has tremendous repercussions on statistics that I'll go into in a later lecture even, so excellent point. The one thing that you do, and if you do an analysis like this, you train a classification algorithm, right? You test it, and then you swap around, let's say you do a 4-fold cross-validation. You have to do it 4 times, right? Because 4 times you've changed your train and test set. So that's 4 times 100,000, right? So that's 400,000 classification training and test sequences. This is going to cost you a lot of time and a lot of CO2. So it's something that, well, I've never done for this reason, because, just end up waiting very long. Okay, just to highlight, that was just one tidbit about, regions of interest in general, and how you can be flexible in terms of regions of interest. This is just to highlight what has happened in this field of MVPA up until, this is like 10 years ago. People still use this, but this is the period when this grew most. And you see, 2012 is also when AlexNet was published, right? So this is really like the old AI being used for fMRI. You see that it really exploded. There's a bunch of these studies that are still the best cited studies in the whole field of fMRI. Because it's pretty cool, right? You can say, we can decode from the brain X. That just sounds awesome. So I want to, like as an intermezzo, show you a few examples of what people managed to do with this approach that just went pretty strongly above what people could do before. So it really does go beyond what you can do with simple GeoIntelligence. So one nice example that I like, because I used to be a researcher in this field more or less, is, I guess I still am, is that you can do this thing called binocular rivalry. So you do some nifty stuff with like glasses that separate the 2 eyes images, and you can end up showing something to the left eye that's completely different from what you're showing to the right eye. And so normally they're in sync, right? You're looking at the same thing. You can be smart about it and trick the brain into thinking that it's looking at the same place in a screen, but then you're projecting 2 different things into the 2 different eyes, like in VR, right? Like in a VR goggle set. And if you make those images completely different, your brain's normal mechanisms that fuse the 2 different eyes' vantage points, images, right? Normally you overlay them and you see depth, right? That's what your brain uses these slight differences for. But if you use stimuli like this, where it's just horizontal patterns versus vertical patterns, then you sort of override that whole machinery and your brain has to choose. Like, there's no way of bringing them together. They're so different, no way. And so what your brain does is it chooses to see one for a while and then switches to the other. And it has this sort of perpetual back and forth between you seeing one or the other of the 2 stimuli that you're being presented with. And this is very cool in terms of consciousness research, of course. You might ask why? Well, you're looking at the same thing all the time, right? And what this means is that because the input doesn't change, it means that your perceptual state, what you are consciously aware of, changes as a function of purely internal processing, right? And so if you can decode what people are seeing at any point in time, where you can do that tells you something about how the brain generates that conscious awareness. Is that clear? So if you have a specific pattern of red and blue voxels here that respond more to the left or the right eye, you can have people then report this back and forth between the left and right eye's image, right? So the people will be reporting like, I'm seeing blue, I'm seeing red, I'm seeing blue, I'm seeing red. And what these researchers then did is take the pattern of activation from V1 for every TR, and then train a classifier to decode what people were seeing, right? And so you see that you can actually decode from V1 in this case, the conscious awareness that people have of a stimulus. Yeah? So from the outside, you would not be able to tell. It's similar to that vegetative state, right? From the outside, you do not see a difference because they're shown exactly the same stimuli for the entire duration of the experiment. Yeah?
For example, as the internal switching happen at a rate that the person is consciously aware of it happening, when you ask them to report.
Yeah, so they know, and that's why how they report. Yeah, it's very hard to get around. Yeah, so I published a paper in 2015 where we tried to get around this, where we made the green and blue very similar, so that people were no longer able to see whether they're seeing the left and the right eye. And we were able to show that these things still happen. So this back and forth still happens. Does that answer your question at all? Yeah, okay. I can send you the paper if you want, but I recommend against it. So yeah, that's beautiful, right? You can actually look inside someone's head, right? And tell from the pattern of activation in their brains what they're perceiving, right? And it's a completely arbitrary thing, right? Their brains made that up. That's pretty cool, I thought. But then again, this is my field, right? So I'm pretty biased. But you can go even further, right? So all we've been thinking about up until now is these yes/no decoding things. You can actually pile on more and more complicated things. So you can go to like more different options, right? So you can do 8 different options, and you can go much further, where you can decode not just yes/no, not just 8, but many different types of outputs. And it turns out that when you do that, when you have that sort of machinery in place, which is quite a hassle, then you can start to do pretty nifty things. So this is a science paper from, I forget when, but not that long ago, like probably 2000. Well, that's not long ago in my book, 2013 or something. So what they did is a horrific experiment where they placed subjects in the scanner, but really horrific. They placed someone in the scanner, and then they would be awake for a while. And then they would have like, I think something like an EEG thing that would tell them when people would enter this, the second sleep stage, right? So you could see people fall asleep from an independent measurement. And then they'd be scanning all the time. And then whenever, like a half a minute or so after they had entered this sleep stage where we think people would start dreaming, they would wake them up. And then after waking them up, they would have to report, like with a keyboard or talking, like say like, yeah, I was dreaming about this, like this thing with a lizard and, you know, whatever. I don't know why I thought of a lizard. Anyway, so they would think like completely random, the stuff you dream about, right? Like I have an example. This experiment, like right now when I explain it, it sounds okay-ish, right? That's cool. But if you look at the methods, it turns out that the couple of subjects that they used for this, they were scanned like up to 10 times, and they were woken up something like 300 times for the experiment, which is kind of horrible in my book. And so you see that they just did this all like over and over and over. Just imagine how you roll out of a scanner after you participate in an experiment like this. I think you'd be pretty damn tired. In any case, so what they would do is just to take whatever happened, whatever people said during that report period, right? So this is like a description of what people would say, like what I was dreaming about. And then they know, okay, well, these are the fMRI TRs, the volumes of data that actually encoded these types of concepts, right? And having enough data, that means that you can train a decoder to relate the pattern of bold activation during these periods to what's being said afterwards, right? And that allows you to train a classifier to see whether you can decode the content of dreams. Yeah. Yeah, he was just like a tad earlier.
How long did they make the people? How long was it?
Yeah, I think like a minute or so, not that long. Yeah. Yeah.
Question about the previous slide.
Uh-huh.
So can we make any inferences by the time that each eye spends on the picture and how the brain activates it, or is it completely random?
Yeah, we can infer certain things. I mean, we have dials to manipulate this process. So if we increase the contrast of the stimuli, generally the back and forth gets faster. But you can also do this between like a house and a face. You normally don't see a house and a face in the same location. So you also get this back and forth. And then you actually see this fusiform, like exactly the orange and blue regions that I've been showing you in that movie of the brain. They actually go up and down like against one another.
I was thinking maybe there's some correlation with the psychiatric diseases, like
Hmm.
you have PTSD patients and you show him something traumatic, maybe he will spend like more time.
Oh, yeah. Yeah. No, that definitely happens. So people have shown that people with schizophrenia are slower in terms of this back and forth. We have, like, I published a paper also at some point where we gave people benzodiazepines, which just increases the inhibition in the brain, and that would make it like slower, and it did. Yeah, so there's a bunch of those things that you can do. Yeah. Does that answer your question? There's like a whole bunch of things that that we know change your perception during that type of thing. Psilocybin makes it faster. Like if you give people LSD, it makes it faster. Yeah, cool. Yeah. No, it's hard, right? Well, this is where the cross validation comes in, right? So what you can do is you can train it on 90% of the data and then let it predict the sort of cloud of words from the left out 10%, right? And then of course you need a measure for like what cloud of words would be produced by a random chance, and its overlap with what people actually reported during those 10%. And I don't really remember how exactly they did it. What this paper is known for is what I'm going to skip to in the next slide, which is just a demo. Which is, you know, this is like demo research. It's like made to produce this demo because of the approach in the research, right? It's about dreams. And so what they did is they trained, they could create like for every TR, they could create like a word cloud. So it's not a yes/no decoding, it's like producing a word cloud and a bunch of images that they would just blend together. And so I'm going to show you what the outcome of one of such trial is. And you could think of how you quantify the performance of a classifier in this way. But that's like a matter of statistics. Yeah.
I was just wondering, like, how many participants did they test at all? Because I thought that sometimes you also have problems to like recall what you were reading about. Like, how many trials when they woke up a participant did they have? And the participant said, I don't know if I can know or I cannot describe it.
Yeah, that's a good question. I think they did.
We like dream, but sometimes when we wake up, we know what people about.
Oh, yeah. Yeah, I think it matters a lot, like when exactly you were woken up, right? Or when you woke up, because if you wake up much later than you're dreaming, like more the strongest dream activation, then it will be harder to remember what, if any, content was there. But here they optimize the experiment to just wake people up always in at an optimal point in time where their brains would still be actively dreaming. Which I think helps with the recollection. But I think they did need to select like a subset of the trials in which there was actual clear recollection of stuff. But there's a host of issues that they didn't get into because this is a demo sort of thing. Yeah. So yeah, good point. Yeah.
So I think the core idea you mentioned, because you're showing two different inputs to the dice, and reality is usually try to switch it together, but it just can't, and hence it tries to. My question is basically assuming this image to a person. Do we see this kind of behavior depending on how the eye naturally focuses on different parts of the image? And that this also can you also look at it as a kind of context switching example in the.
Yeah, like a sort of information foraging sort of thing, yeah. Indeed, yes, high salience portions, people have done variants of this type of thing where images that are highly salient and locations in an image that are highly salient will actually win this battle between the eyes sort of thing more often and more quickly than like low salience parts of an image. So there is something to salience that gives an image a stronger influence in this back and forth process. Yeah. We can talk more about this later, but it's not brain imaging, so I'm gonna have to, in any case, I'm gonna show you the outcome, right? So the word cloud's at the bottom. The at the top is like the sort of picture cloud that they made. And here you see the time to awakening, and it's going to count down, right? And then at the end, it's going to give you what the person said, right? So this is just coming from the decoder. I don't know where they came up with mercantile establishment. Pretty nifty, right? As a demo, it works. You can brain read, right?
Is the word cloud you see at the bottom, is that from all the trials combined, like the most
It's trained on all files combined, yeah.
okay, so that's kind of the dictionary they're using for their specification.
Oh, I don't know if they're using like a cutoff somewhere. Like I'm assuming that there would also be other words in their word cloud.
Yeah, exactly.
Yeah, possibly, yeah. Yeah.
Are they generating the images themselves from the brain, or is this just like a?
I think this is a lookup table sort of thing. Yeah, like the words, it's a lookup table, yeah. Okay, so this is cool, right? It's a demo. And I'll hope to be able to get into why this is a demo and how we should think about the actual science content after I show you the next thing. So that's just a couple of applications of this multi-voxel pattern analysis that people have used. It's all like about 10 years ago, but you can definitely see how this became a hype, right? Brain reading, right? And then this sort of thing, like you can look inside someone's head and then tell what they're dreaming, right? It's like pretty awesome if you can pretend to be doing that as a scientist. But we need to always be critical about like, what does it really tell us about brain function, right? And there's, for example, I'm just going to give a bit of this away because I'm afraid I might not have time, but there's a region in the visual cortex called the visual word form area. Whenever this activates, you're reading, right? And so during sleep, if it activates more than the the surrounding regions, then you're likely dreaming of text, right? And so this whole word cloud, it looks very complicated and very sort of intricate. It doesn't have to be based on a lot happening in the brain, right? So this sort of demo material does give us a beautiful feel for what we're doing brain reading. The actual level of detail is a bit up for grabs. Okay, so those are a few applications. And now I'm going to talk about one sort of approach to pattern analysis that can sometimes be based on decoding, but tries to take it a step further. And more so than standard multivoxel pattern analysis, this has the pretense that it actually tries to sample how the brain represents information. And we can argue a bit about that, and I hope to, we might not make it all the way there during this lecture, but we can definitely get there, perhaps during the practical and further lessons. Lecture. But this is called representational similarity analysis. There is a reading assignment on Peruso that goes into this. So what is it like? What is this representational similarity analysis? This is not meant to scare you. It's a lot of information on one slide. I'll go through it very slowly. So at the top, you see a whole bunch of different stimuli that were shown to observers that are in a standard representational similarity analysis type. Experiments shown to observers. And you see a whole bunch of different visual images, right? So this is all visual images stuff. You see bodies without heads, you see faces, you see of humans, you see non-human bodies and heads, and you see natural objects and artificial objects. So you have objects versus agents, if you will. And you have animate versus inanimate and human versus non-human. Pretty nice. So in an analysis like this, what you do, you take a region of interest in the brain, as you do here, and you extract the voxel activation pattern. So here you see they just stretched it out into a single vector. It's not the shape of the region of interest anymore, but that's just what happens when you take a Boolean mask, like you learned from the first practical, right? So you take that vector of responses from the region of interest, and now we can do a decoding analysis on this pattern in the vector, right? And so what we can do is actually get this pattern for 92 different stimuli, right? So we don't have 2 different stimuli, but we have 92 different stimuli, right? And how do you then work with this? Well, you don't have a single pattern type analysis that you're doing between 2, but you have all possible combinations between those 92 different stimuli. So you can do a decoding analysis between stimulus 1 and 2, between 1 and 3, between 2 and 3, and so forth, right? All pairs you can go through. Yeah? And what you'll be able to see is whether in this region of interest, stimuli I and J are processed similarly or not. Yeah? So because you have so many stimuli, in this case almost 100, you have this entire sort of dissimilarity or similarity matrix that you can fill up with all of the different pairs of different stimuli, right? So one specific value inside this matrix, like 1 pixel, could be, is the processing of a kiwi similar to that of a brown cat, right? Or any other combination. Yeah. So there's this is something that was sort of devised by this dude Nico Kriegeskorte, and you'll be reading this TICS review in the Perusol thing. Now, what does this give us? Yeah, what I'm showing you here is an example of how you do that on an fMRI voxel. Yeah. But the nice thing about this sort of thing is you can do it on almost anything. And so let me highlight what that means. I could also do this from a pattern of electrode activations in visual cortex, in the inferotemporal cortex of a monkey, for example. That also gives us a pattern of activation. Right? And if I show the monkey the same stimuli as I do the set of humans, what this will allow us to do is create a matrix, the same thing, like inanimate, animate, human, not human, right? Same matrix, it's filled up. You see that it's symmetric, because any comparison between I and J is also the same comparison between J and I. You can get that from monkey IT, and you can get it from fMRI in human IT. And here you see the sort of power of this analysis. You're starting to get a handle of why you would even go here, right? Up until now, it felt like, yeah, you're just exploding the problem. What are you getting in return? Well, what you are getting in return is the possibility of using this sort of space, this representational similarity matrix, to compare between different things. Right? So I can compare whether the monkey IT represents this set of stimuli in a similar way to human intratemporal cortex. Yeah. And you'll read in the paper that you can go much, much further. You can also do this on a neural network. Right? You can just take the activation pattern in a neural network for this set of stimuli, construct a representational similarity matrix. You can do it for the different layers in a convolutional neural network if you want. And so you can then start to see which regions in the brain process information in a similar way to different species, to different neural network models, and so forth and so forth. Yeah. So this gives us a beautiful playground to look at representation in the brain. Yeah. Now, it's important to realize that it is kind of arbitrary. Yeah. This whole thing depends on the set of stimuli that we're using. Yeah. And so if that is very limited, we only have a very limited view on how information is being represented. And so what's beautiful here is that this is just to get into the specifics of what you're doing. You can compute for a given region of interest the similarity pattern. All right, you fill that in a specific region, and you can have all of these different representations, so different sources of information that allow you to compare information processing between the origins of these sources of information, right? So between the monkey, between the human, between different regions of interest, between different time points, anything. Because you have always this pairwise structure of comparisons of patterns, you can compare anything with anything. And the beautiful thing is, it's not just anything that you're comparing, you are comparing something related to the geometry of how information is represented in the brain across a certain set of stimuli. Yeah? Yeah, so generally when you look at the figure in a paper, that would be averaged across subjects. But all of the core analyses will be done at the single individual, single ROI level. Yeah. Is the concept clear? If there's anything that's crucial that you need to know, ask me now. If there's anything that you think like, it can wait, then you'll read about it in the review and we can talk about it later. Does that sound good? Because I wanted to show you this this example that I really like. It's this paper published in 2014 in Nature Neuroscience. It's one of the, I think, very nice showcases of how this representational similarity analysis can be used as a sort of Rosetta Stone to translate between different modalities of measurement. Yeah. So it gives us a sort of standard standard space in which we can quantify a representation of information. And because it's always the same, regardless of where the information came from, we can actually use it as a sort of translation step. And so in this paper, which I really like, it's a bit of a parlor trick sort of thing, but it is very, very nice. They've done this type of, they use the same stimuli here. And they didn't use only fMRI for this. So they didn't just use a pattern of voxel activations in some region of the brain. What they did is they did exactly the same experiment, but they did it using fMRI. And they also did exactly the same experiment using MEG, which is magnetoencephalography. And it's much faster. It's one of those brain reading methods where you lose in terms of spatial resolution because you only have 306 channels over the head, but you gain in temporal precision. So you have millisecond by millisecond measurements of brain activation. And here, what you can do is not just use the pattern of voxels or different regions of interest. Here, you can then start to do this representational similarity analysis every millisecond after the onset of a visual stimulus. So you can have a different representational similarity matrix after 100 milliseconds, after 110 milliseconds, after 120 milliseconds. So you can actually look at the temporal evolution of this representational space. But you otherwise treat the sensor pattern exactly as if it were a region of interest in visual cortex, for example. Yeah, so it's just a pattern of activation. You do this whole classification thing, and you end up with this representational similarity matrix. Same, exactly the same. So what does this look like? You must be thinking like, oh, okay, dude, why did you just switch to MEG, right? I'll get there. And so what you can then see is from this sort of representational similarity matrix, you can, then the evolution of that representational similarity matrix, you can get a handle on the time course of how information processing happens, right? So you see that very early on, you see there's a lot of, you start to get this sort of blue patch here. And it means that there's a lot of face processing that's happening that's similar. Just in general, you see that there's a decoding accuracy that peaks around 120 milliseconds. And you see that certain types of information processing, such as those about natural versus artificial stimuli, natural takes longer, right? There's prolonged decoding accuracy over time, right? So here we're not looking at fMRI because we are interested in time, right? And these specific parts of the representational dissimilarity matrix, tell us something about, for example, the difference between natural and artificial, that sort of thing. Yeah, is that clear? So these patches inside the representational dissimilarity matrix, they tell us something about the type of information that's now contributing to the representation pattern in a certain region of interest or at a specific point in time. Now, why am I showing you this? This is MEG, it's all about time. Thomas, you're not supposed to care about time. You're this fMRI person, so why are you doing this? It turns out, but doesn't just turn out, they actually also did this experiment in fMRI, like I told you, right? And so what you can then do is you can take the representational similarity matrices from the MEG at different milliseconds, and then try to look at them in terms of their correlation with patterns in V1 and inferotemporal cortex from the fMRI. Yeah. And here we're using that representational similarity matrix as this Rosetta Stone, as a translation tool. Yeah. You can start to say, well, if V1 is earlier on in processing, right? This means that the representational similarity matrix that I get from V1 should be very quick, right? It should correlate with very quick responses in the MEG, whereas this inferotemporal cortex region that has all of the interesting information regarding animacy and inanimacy and objects and humans, it should peak later. And that's exactly what you see, so that you have all of these representational similarity patterns from MEG for every millisecond. You correlate them with V1 and IT. You see that the V1 activation pattern is similar to very, very quick MEG responses, whereas the IT representational similarity matrix actually correlates best at much longer timescales. If you look at the difference, you really see this sort of going from low-level information processing, like we have in V1, to more high-level, sort of conceptual information processing later on in the time course. So what I hope this gives you is an idea for how such representational similarity matrices can be a very powerful tool in translating between different modalities. Yeah. And they can be this sort of Rosetta Stone, if you will. Now, people, and in the review, you'll read this, people have come up with a lot of different ways in which you can think about the structure in these representational similarity matrices. I don't really have time to go into that. I do want you to see a demo that they've created where they haven't actually just used the V1 and IT regions of interest. You can actually do this analysis on a searchlight basis, so that you actually have a representational dissimilarity matrix for every voxel in the entire brain. And so then your question becomes, can I correlate, for example, this voxel's representational similarity matrix with all of the time points in the human MEG representational similarity matrix, right? So you really get an information processing time course for every voxel in the brain. And this is why I think this example is really powerful, because it shows you how you can sort of multiplicatively combine two different sources of information. You're using the MEG for the time, you're using fMRI for the space, and what you get out, in this case, is space-time, right? So you have a temporal, you really have a time course for every voxel in the brain by combining them in this way, by sort of shoehorning them into the pattern of this representational similarity matrix. And so what I want to show you here is how in space information processing transpires. So this is the fMRI signal, but then the correlation with the MEG signal over time. This is the actual MEG RDM, the representational dissimilarity matrix. And this is one of the things that you can do with a matrix like this. It's called multidimensional scaling. And what it allows you to see is how different, how the structure in the representational dissimilarity matrix evolves. So you'll see these types of, you see things like faces, bodies, and inanimate objects start to cluster at certain time points. I won't go into the specifics of this multidimensional scaling. It's not that complicated, but you'll see these things starting to cluster over time. So this is a movie that I will play. So here you see this, I think I have to play both. So this one is, oh geez, wait. Here we go. Yeah, so they're sort of both, they're offset, shit. So you see that at 80 milliseconds, things are happening that are very similar to V1. And then as you move forward in time, you see that the pattern of activation starts to look a lot like ventral visual cortex, like the more category selected cortex. You also see that over time, all of this structure is emerging in this representational dissimilarity matrix. You see that these the categories are starting to bunch together, right? And what that means is that at that moment in time, processing regarding things like facial identity and what have you are taking place in not just this point in time, but also this point in space. I mean, try that again. Somehow, didn't yoke these things, but yeah. So you see how we can bring together these different types of measurement modalities by all shoehorning them into this similar, into the same experiment, projecting all of the patterns of activation into this representational similarity space, and then seeing how different measurement modalities relate to one another. And in this case, it allows us to multiplicatively combine the strengths of these two different measurement approaches, right? We have space from fMRI, we have time from MEG, and we now get both. So this is a very innovative way of using imaging in general, right? Just taking in two different types of measurement. But this is one of the things that this sort of thing allows you to do. Now, quickly to recap, right? What's nice about MVPA in general and all of these methods is that it has allowed us to go beyond just activation, right? This thing about localization. And it moves us away from that activation towards thinking about information processing, which is beautiful. We are actually answering questions about how the brain represents specific types of information. And that is a very valuable step to have taken. So we're going away from that question, where in the brain, we're now answering the question, where can we find information about X and not just activation related to X? We're also asking questions like how similar are stimulus X and Y in terms of how the brain entertains them. It also gives us a lot of more power because things that didn't really pop out as a result from GLM analysis, they might have a consistent pattern of activation associated with them, if not a mean difference in activation, and thereby make us more sensitive. Yeah. But even on equal activation, we can still find that there is representation there. And what's also beautiful, I think, is that if we use RSA, we can actually start to compare between different modalities. We can, modalities being different species, between MRI and MEG, between electrophysiology and fMRI, and so forth and so forth. So it's a very powerful approach. Yeah, just tilting slowly from activation and blobology to thinking more about information processing. And that's really where we want to be. But this wouldn't be brain imaging if there weren't some caveats also. Right, so we need to think deeply about where are we now? And so let's assume that you're doing this searchlight analysis. What you get is a classification accuracy for all parts of the brain, right? And that will give you a p-value in the end, or a t-stat, also for every voxel in the brain. And this means that if you do this type of analysis, you may be more sensitive than you would be in a standard GLM sense. You still end up with the same problem that I showed you in one of the earlier slides, where you can have a threshold. If you raise it very high, you get a single location. If you raise it more low, if you raise it more low, geez. If you take it down further, you'll start to see more and more regions pop up, right? And then you're stuck with this network idea. It still doesn't allow you to adjudicate between these types of different processing. Yeah? You're still looking at things like significance for this sort of thing. Yeah? Now, and this is a very important one. I haven't really gone into this, but I do want to highlight it here. We've now sort of delegated all of the hard work to some classification algorithm. We don't know what it does anymore, right? We just know it's a complicated algorithm and it is very good at picking up patterns. And we don't care what the pattern is, as long as it gives us a percentage correct that's above chance, right? And so this whole field is always just testing things against chance, right? It's a very hypothesis-driven type of thing that lets the hard work be done by some algorithm. It's not very interested in the exact pattern of activation, right? And so it stays a bit removed from actually explaining what the computations are that should give you this pattern, right? So you're sort of blind to why that pattern arose in the first place, because you're letting the heavy lifting be done by a classification algorithm, right? So that's leaving the hard work to an algorithm. And the downside of that is that it makes you as a researcher relatively blind to what's actually going on, right? So you can be victorious in claiming that some type of processing is happening in some brain region, but you don't yet know what that processing is about, right? Well, you know what you sort of know what it's about, but you don't know how it works yet. And so that is conceptually a bit problematic in the way that people have used this type of approach. And so one solution to this problem, right, of remaining blind is to do more of the heavy lifting yourself, to create an explicit model of how the brain produces patterns, how the brain produces its responses and thereby patterns. And that gives you not just an explicit model of computation that you can compare, but you can then really get a handle on how the brain represents information. We'll talk more about that in one of the next encoding model lectures. And one thing that I think we also want to think deeply about is how this idea that we had, if we ask a specific question like, is fear here or where is fear? It presupposes that the brain uses fear as a coherent concept to structure itself, right? And is that the case? Well, in many cases in these decoding approaches, in this classification type approach, what people do is they have these two options, like the car and the face. Yeah? And you can find decoding there, but you're sort of dependent on the fact that this categorization holds, right? And that the brain adheres to it. And so this is also a sort of trap, right? You can get stuck in it if the brain doesn't really care about how you categorize things. So the question here, does your scientific question presuppose a specific structure of cognition? right? And how robust are you when the brain decides, yeah, it's nice and all that you think fear is important, but I think fear, arousal, and laughter are all very related, and I just do them all together. So up yours, right? The brain could be organized in this way, and then you as a scientist would have a major problem, right? You're sticking to your concepts too much. And this is something of a danger if you apply this MVPA in the way that people have generally done it. Again, this is something that's that people have moved away from, but this was a sort of, you've seen the thing, right, from 2006 to around 2013. This is really what people were engaged in a lot. And people are using it in more sophisticated ways. I hope the MEG fMRI experiment was an example of how sophistication was added over time. And then in subsequent lectures, we'll move more towards these modern ways of going about this, things like those explicit encoding models. Your question?
Yeah, I think you kind of answered it. Basically, the similarity matrix is a pretty good tool, I thought, to find out, okay, how does the brain actually extract information? Because then we have all of these examples, and then we can see how can we best categorize. So that would kind of be a solution to our question.
Yeah, you're letting the brain sort of show its structure without imposing some binary distinction, beforehand. Although at the same time, 92 images is not that much, right? You need a whole lot more to train AlexNet, for example, right? And so you're also, again, you're restricted, right, in terms of the space that you were able to span with an approach like this. Yeah. Any other questions? Because then I think we have a break, and then you can all come back here for the practical, I think it is, right? Excellent. I'll see you guys in, what is it? 4 minutes? No! Yeah.
Do you want to be a part of the fMRI experiment at the Spinoza? Or
Really? That's a good thing.
I'm trying to find the one you were talking about, like the psilocybin one.
Oh, yeah.
Do
Wait.
you know where I can find it?
Yeah, I think I have materials. I have to search for a while. I have to look them up. They're in my.
Because I have like the.
Yeah, I don't think it's
Look
let me see. I think I have a. So much stuff in these things. Oh.
Is that the display?
Oh no, this is a like this is called Zulip. It's but I think our PhD student, he put in like the materials at some point. But maybe it's somewhere else.
And also, are you allowed to get the data? Like, could you get the pictures of your brain?
Not immediately. You might get them later. I don't.
Okay,
Yeah, not.
after it's published.
Wait. I got it here. There's I'll just drop it in bits and bobs. I'm dropping it.
Bits and bobs. Okay,
Wait, where is
in
it?
Discord. Right? Yeah.
Yeah.
Okay, nice.
How do I send it, man? Huh.
Thank you.
Yeah. Oh, yeah. Dan, ja, dat is wel handig. Ja, zullen we dat even... volgens mij ben ik nog op Zoom.